Hi, it's Ants. This is part 5 of the series Why You Should Not Use libGDX for 3D Games. Well, I got some hate mail with regards to part 4 of my video series, which basically outlines how poor the web builds perform compared to the execution on native Java code on the desktop. And I got some hate mail, and they basically said, that's just one example. It's not indicative of the general performance of anything, and you can't make assumptions based on one project. And I've said, okay, that's interesting. Actually, that's pretty good. So this is the reason why I'm doing another example. But this example actually proves that it's just GWT. TVM actually performs really well. So the model cache example basically points to in the previous video to libGDX to GWT emulated math classes, the way they set up. It may be setting up GWT for failure. I don't know, but the culprits are math classes like longlib, big longlib, but int map. They're taking up like a huge chunk of time, and also there's 2016, and there's an issue where after GWT 2.7 to 2.8, they noticed a 70 to 80% slowdown of long bitwise and emulation of long numbers, and they did nothing about it. They said, we're not going to regression test, and that's the way it is. And it rarely happens today. I mean, the way, if you read this this issue, it's like, okay, whatever. But anyways, I'm not going to get into detail here. I'm going to basically continue on of how Franziska Henkelmann, the PhD math graduate who works for Google, and she presented in 2019, where she basically says, listen, JavaScript performs twice as slower than native C++ code, and WebAssembly based on that C++ code is just slightly slower. And so your Java code should only be twice as slower, and that's what you should expect. And I'm going to go down the path that she laid out, and I'm going to have another example that does not use any libGDX classes. It's just using Java, and it's just using for loops and just logic, basically. And I'm going to show you that still on very simple example, GWT is 6 to 7 times slower, and gdx-teavm is 1.2 to 1.3 times slower. So it's similar to the WebAssembly output, right? So which algorithm am I going to use, right? So that's a good question. So I'm going to use a very old algorithm, but it's extremely efficient to basically count or generate all the primes smaller than equal to 0 to 2 million. I'm using 2 million, and it's called, hopefully I pronounce it correctly, sieves of erotothenines. And it's 2,000 years old. Sorry, my screen blanked out. And it's quite simple, actually. It starts with the first prime number 2, and then it gets all the numbers which are divisible by 2, and it marks them all as not being primes, i.e. not primes. And then goes to the next number 3, and it does the same with that. It basically marks all the numbers that are divisible by 3, like 3, 6, 9, 12, but 6 has already been done, and it goes on, and it does that. And then by the time it gets to a pretty high number, it actually figures it out pretty quickly. It's extremely efficient here. It's always n times log of log n. The only problem here is the space, where if you have 2 million numbers, you have to store 2 million numbers in an array. Now there's different ways around that. It's called segmented sieve, but I'm just using a very simple algorithm, and it comes with C# versions and C++ version. It's exactly the same. It's very simple, actually. So let's get started with this algorithm. So let's go to Android Studio or IntelliJ, whatever you want. And here is the algorithm. As you can see, it's not that many lines of code. And this one here, it looks like it's a nested for loop, but it's this that checks to see if it has it been marked. Is it still a prime? Do we still suspect it's a prime? And if it's not, it doesn't even go into this. And this is the reason why it's so efficient, is because after it does 2 and 3, you got a large chunk of the number set already marked as not a prime. So it never goes into this, I shouldn't say never, it hardly goes into this other loop over here. And this other loop actually checks to see if the current prime number searches all the remaining numbers that are divisible with that number and all that kind of stuff. But anyways, regardless, it's extremely efficient. So let's run it. And let's mark down some times. And here's the desktop, and it went to my other monitor. And it's 3 to 4 milliseconds. I don't know if we should use 3.5, but I saw 5, but it's mostly 3 to 4, maybe 4 milliseconds is in the between. Let's go with 4 milliseconds, desktop. Okay, I wrote that down. Oh, let's make it bigger so you guys can see. It's desktop, it's libGDX, 3 to 4 to 5, so I put 4. Hopefully you guys are okay. It doesn't really matter. I mean, you'll see what I'm talking about. Let's run the HTML version, right? And I pre-built it because it takes 31 seconds to build. Now, this execution is much more varied, which is a major problem there too. So it's 20 to 30, right? So let's use 25, I guess. 25 millisecond GWT. Again, I might be off by 1 or 2 or whatever. It doesn't really matter because it's slower. We all already know that. And let's try, oops, I went ahead of myself there. And let's try TVM. All right, that's TVM. Let's open in browser. So it's going to get faster, 5 to 6. It's, yeah. So let's put it as 5.5. I mean, like, yeah, we're just splitting hell. So let's get the calculator out. Okay, so the GWT took 25 milliseconds divided by 4 for desktop, 6.25. Remember how I said on the slide it's 6 to 7 times slower? This is GWT, proven that it's between 6 and 7 times slower. It's all over the map too, which I don't like either. I'd rather have like a slow number, but it's a constant slow number. Having it varied like that, suspect. Let's clear this. The TVM was 5.5 divided by 4. It's 1.3, 1.2, 1.3. Again, when it's such small numbers and we didn't get an exact number, it's around that ballpark. It's actually quite fast. So what this shows is GWT is still a major problem, but TVM, if it just uses Java classes, just straight up Java, it's fast. Keep that in mind. However, with the model cache, it actually shows that something else is kind of causing that. But I'm not explaining why that. I don't know why it's slow. I just know it's slow. So let's compare this now to other alternatives and other game engines. And let's do C#. So this is C#. And you can mix C# with GDScript. So I put this algorithm using C#. As you can see, it's very Java-like. Let's run this. Right? It's the same sort of algorithm. Let's run this. So C# is 14 to 15. I'm going to take the higher number. I'm going to take the higher number so that I make it slower on Godot. So calc 15 divided by 4. So C# is 4 times slower than native Java code. That's not great. That being said, C# is not a good programming language of Godot anyways, because you can't export C# code to the web. And so for me, I'm not going to use C# because I export my projects to the web. But there is C++. And here's C++. I created a GD extension. It's actually easier than I thought it would be. Here is the actual code that I used and compiled into GD extension that compiled to 1.53 kilobytes. And we could export this to the web, but let's run it under desktop. And this is between 3 and 4 milliseconds. It's faster than Java, but 3.5 compared to 4 milliseconds, it's not that much of a difference, but C++ is faster than Java, which we kind of expect that. I mean, C++ is going to be the fastest code. But here's the kicker. Here is like, and I'm glad that you stayed long enough in this video to give you this important information. It's just as fast on the web. The generated code using WebAssembly of this, and I'm going to show you this, I'm going to prove it to you, it's going to be 3 to 4 milliseconds also on the web. Okay, so let's export to the web templates here, export project, save. Okay, as you can see how fast it actually compiles the web project compared to other frameworks. And let's stop the web server. I personally think that it's faster on the web than on desktop, because the desktop version is doing something like a JNI call. Like, it's actually, there's overhead for GD script to call the library. It's 3 to 4, but honestly, I actually see more 3 than 4. So either way, let's all agree that it's just as fast as C++ compiled code on the desktop, and you get that performance on the web in your browser. Absolutely fantastic. So that's basically it. I hope you enjoyed that. Let's go back to the slide and show you these numbers. So yeah, so web projects in Godot basically run at the same level as C++ code, which runs faster than desktop Java code. So it's actually faster than the Java code, even the web version. But anyways, regardless, this is about libGDX. Something's wrong with GWT. We all know it. Everybody knows it. Nobody talks about it. Nobody talks about the quiet things out loud, and they blame GWT. But does it really matter who blames? And by the way, I was going to do a video called excuses, like, the blame game and all that kind of stuff. Or we don't have funding, we don't have this, and these are just excuses. And that's probably going to be my last video. And that's basically it. So anyways, hope you found that interesting. I did. And one of the things that I love is I learned how to do GD extensions, which is actually quite easy. And it's super fast. And I'm very excited using C++ and GD extensions within Godot. And yeah, so anyways, hope you enjoyed that. Take care. Bye.